What if I told you that our solar system is surrounded by a 50,000-degree wall of fire? In 1977, NASA launched the Voyager spacecraft on a mission to explore the outer planets. Decades later, they journeyed beyond our planetary neighborhood and pierced the veil of interstellar space. What they found there was completely unexpected and reshaped everything we thought we knew about our place in the galaxy. It's a story of incredible engineering, surprising discoveries, and humanity's first true steps into the cosmic ocean. Let's explore this together.
The mission begins.
What if you launched a mission planned for 5 years, and it was still sending back groundbreaking data almost 50 years later? That's the story of Voyager. In 1977, NASA launched the twin spacecraft Voyager 1 and 2 to take advantage of a rare planetary alignment that happens just once every 175 years. This grand tour alignment allowed them to use gravity assist to slingshot from one gas giant to the next. The mission was overseen by project scientist Dr. Edward C. Stone, who guided its scientific vision for an incredible 50 years, from 1972 until 2022. His leadership was pivotal as the mission's scope expanded far beyond its original goals of studying Jupiter and Saturn. Voyager's instruments revealed the first active volcanoes beyond Earth on Jupiter's moon Io and the complex braided nature of Saturn's rings. Voyager 2 then went on to give humanity its first ever close-up views of Uranus and Neptune, discovering new moons and powerful winds on these distant ice giants. Beyond the science, the mission also carried a message: the Golden Records, 2 phonograph records containing sounds and images selected to portray the diversity of life and culture on Earth. Dr. Stone and the team ensured that Voyager was not just a scientific probe, but an emissary to the cosmos. This dual purpose has made its journey one of the most profound in human history.
Journey outward.
Imagine being on a ship sailing into uncharted waters, leaving the familiar coastline behind for an endless ocean. That's essentially what the Voyager probes were doing. After their spectacular planetary flybys throughout the 1980s gave us our first intimate views of the gas giants and their dozens of moons, the Voyagers just kept going. Their trajectory was carrying them towards the edge of the sun's influence, a theoretical boundary that no one had ever directly observed. As they traveled farther, their instruments continuously measured the solar wind, that constant stream of charged particles flowing from our star at 1,000,000 miles per hour. As expected, the solar wind grew weaker, and its density thinned. This data was crucial for scientists like Dr. Alan Cummings, a cosmic ray physicist at Caltech who has been with the Voyager mission since its inception. He and his colleagues were watching for the moment the solar wind would finally succumb to the interstellar medium, the tenuous mix of gas, dust, and plasma that fills the space between stars. The journey was long, and the signals grew fainter, but the anticipation within the scientific community was immense. These probes were about to answer one of the most fundamental questions we have: where does our solar system truly end?
Crossing the Heliopause.
Imagine being the first to cross a frontier that was, until that moment, purely theoretical. In August 2012, that's exactly what Voyager 1 accomplished. After a 35-year journey covering more than 11 billion miles, it finally punched through the heliopause and entered interstellar space. Its twin, Voyager 2, followed a different path and crossed the boundary in November 2018. This second crossing was vital, confirming the findings from a different location and time. The moment of crossing was confirmed by several instruments, but the smoking gun came from the plasma wave subsystem. Dr. Donald Gurnett, the instrument's principal investigator, analyzed a distinct signal: a clear vibration caused by the much denser plasma of interstellar space. Gurnett described it as hearing the sound of interstellar space, a persistent hum that proved Voyager 1 was no longer in the tenuous solar wind but was now flying through the denser medium of the galaxy. This was a monumental achievement in human exploration, turning the abstract concept of the heliopause into a measurable, physical place. For the first time, a human-made object was directly sampling the stuff between the stars, and the data it sent back was about to get very, very strange.
The Wall of Fire.
Now, here's where the story takes a truly wild turn. As the Voyager probes punched through the heliopause, their instruments detected something that, honestly, stunned the scientific community. They registered a massive and abrupt spike in plasma temperature, from just a few thousand degrees to a mind-boggling 30,000 to 50,000 Kelvin. That's up to 90,000 degrees Fahrenheit, which is actually hotter than the surface of the sun. This phenomenon was poetically dubbed the Wall of Fire. It's not fire in the way we know it, but rather a region where the solar wind, after its long journey, effectively slams into the interstellar medium. This cosmic collision compresses and energizes the plasma particles, heating them to these extreme temperatures. Dr. Stamatios Tom Krimigas, the principal investigator for the low-energy charged particle instrument on both spacecraft, saw the data come in firsthand. His instrument confirmed that the particles in this region were incredibly energized. This discovery showed that the edge of our solar system isn't a gentle fade into the void. It's a violent, superheated interface where two cosmic winds clash.
A superheated frontier.
You might wonder, how could a spacecraft survive flying through a region that's tens of thousands of degrees hot? The answer lies in the critical difference between temperature and heat. Temperature measures the speed of particles, while heat is the amount of energy they transfer. While the particles in this wall of fire are incredibly hot, meaning they are moving at immense speeds, the plasma itself is incredibly sparse, far less dense than the best vacuum we can create on Earth. We're talking about fewer than 1 particle per cubic centimeter. Because the density is so low, these super-fast particles almost never collide with the spacecraft, meaning almost no heat is actually transferred. Dr. John Richardson, the principal investigator for the plasma science instrument on Voyager 2, was instrumental in analyzing this data. His team's work showed that while the temperature was extreme, the pressure was negligible. It's kind of like the difference between the air in a hot oven and a drop of boiling water. You can put your hand in the oven for a moment, but the water would instantly scald you because its density allows for rapid energy transfer. This superheated low-density frontier provided our first direct evidence of this turbulent, transitional layer, where the sun's influence finally yields to the vast expanse of the galaxy.
The dynamic shield.
The discovery of this superheated boundary also revealed something pretty profound about our place in the galaxy. The heliosphere, this giant magnetic bubble our sun creates, acts as a critical protective shield. It deflects about 70% of the high-energy, galactic, cosmic radiation that constantly bombards us from deep space. This radiation is harmful to life and can fry spacecraft electronics. The intense heating at the Heliopause is a direct consequence of this shielding process. NASA compares it to the bow wave formed by a ship cutting through water, a buildup of pressure and energy at the leading edge. The latest models, developed by scientists like Dr. Merav Ofer at Boston University, suggest the heliosphere isn't shaped like a classic comet with a long tail. Instead, her work, using Voyager data, indicates it might be shaped more like a croissant, with two large jets curling away from the direction of motion. This shape is likely formed by the interaction between the sun's magnetic field and the magnetic field of the local interstellar medium. Understanding this dynamic shield is crucial for protecting life on Earth, and honestly, for future deep space missions.
Magnetic mysteries.
Imagine expecting a sharp, dramatic change at a boundary, only to find a smooth, almost seamless transition. That's what Voyager discovered about the magnetic fields at the edge of our solar system. For years, scientists had predicted that the magnetic field inside the heliosphere, which is carried outward from our sun, would be oriented very differently from the interstellar magnetic field. The prevailing models suggested that as the spacecraft crossed the heliopause, it would see a dramatic shift in the field's direction, a phenomenon known as magnetic reconnection. But that's not what happened. Dr. Norman Ness, the principal investigator for the magnetometer instrument on Voyager 1, was at the forefront of this surprising discovery. His instrument, a sensitive device on a 13-meter boom, found that the magnetic fields on either side of the boundary were nearly parallel. This unexpected finding implies a much smoother connection between the solar and galactic magnetic environments than anyone had predicted. Instead of a sharp, defined edge, the boundary appears to be a more gradual blending zone where the sun's magnetic influence slowly intertwines with the larger magnetic field of our local galactic neighborhood. The mystery of why these fields align so neatly is still a topic of intense debate today.
Cosmic ray barrier.
Another critical function of the heliosphere is to act as a barrier against cosmic rays, those high-energy particles accelerated by distant supernovas. The data from the Voyager probes has given us an unprecedented, real-time look at how this barrier works. As the spacecraft crossed the Heliopause, their instruments detected a dramatic and immediate increase in the number of galactic cosmic rays, while the number of lower-energy particles from our Sun dropped to nearly zero. This was the smoking gun that proved they had left the nest. Dr. Jamie Rankin, a research scientist at Princeton University who studies this phenomenon, uses this data to refine models of how the heliosphere acts like a semi-permeable membrane. It deflects most incoming cosmic rays, but some still get through, and the number that penetrates is directly related to the Sun's 11-year activity cycle. When the Sun is active, the shield is stronger. When it's quiet, more radiation gets in. This knowledge is not academic. It directly impacts our understanding of the radiation environment for astronauts on future missions to the Moon and Mars.
Interstellar space.
What is the shape of the bubble that surrounds our solar system? For a long time, the prevailing theory was that the heliosphere was shaped like a comet, with a rounded nose and a long, trailing tail stretching for billions of miles behind it. But the data from the Voyager probes, combined with observations from other spacecraft like Cassini and Ibex, has challenged this simple picture. Dr. Merav Ofer, a leading heliophysicist, has used this data to create new models suggesting the heliosphere may not have a long tail at all. Her research suggests a shape more like a deflated croissant, with two large jets of solar material flowing downstream, shaped by the pressure of the external interstellar magnetic field. This new model is still being debated, but it shows how Voyager continues to fuel new scientific inquiry nearly 5 decades after launch. The faint signals from the probes, traveling for over 22 hours to reach us, provide our only direct measurements of the interstellar medium. This information about plasma density, magnetic strength, and cosmic ray intensity is the ground truth against which all our theories about our cosmic home must be tested. Each bit of data is precious, a postcard from an unknown shore.
Future missions.
As incredible as the Voyager mission has been, it is fundamentally a product of its time. The probes were built in the 1970s, and while their longevity is a miracle of engineering, their instruments are limited by today's standards. That's why NASA is already looking ahead. A proposed mission, tentatively called the Interstellar Probe, would be a dedicated successor designed to explore the heliosphere and the interstellar medium in far greater detail. Dr. Ralph McNutt of the Johns Hopkins Applied Physics Laboratory is one of the leading scientists behind this concept. The plan is to build a probe that could travel much faster than the Voyagers, perhaps reaching 1,000 astronomical units in just 50 years. Equipped with a suite of modern sensors, it could map the full three-dimensional structure of our heliosphere and analyze the interstellar medium with unprecedented accuracy. This mission could finally answer the lingering questions from Voyager, like the true shape of our cosmic bubble and the nature of the magnetic forces at its edge. It represents the next great leap in humanity's journey to the stars. From a grand tour of the outer planets to a journey into the interstellar void, the Voyager mission has fundamentally rewritten our understanding of the solar system's edge. It revealed a dynamic, superheated frontier, a place not of emptiness, but of incredible energy and motion. The two probes, now nearly 50 years into their mission, continue to send back faint whispers from the darkness, each signal a new piece of the cosmic puzzle. Though their power will one day fade, their legacy will endure, carried on the golden records that drift silently between the stars. Don't forget to like, subscribe, and hit the bell icon for more journeys to the frontiers of science. Thanks for watching Stellar Tech.